All right, so I just checked. The movie is called Awakenings. It was in 1990s when it came out, and it's based off of a doctor back in the 60s. So I had pretty much all those details correct. So like I said, it's a great movie if you are thinking of going into the health field. Again, it was based off of a true story, and here's a perfect example of learning about it. Okay, 15.6, Fischer projections. All right, Fischer projection. Fischer was, Emil Fischer was kind of like the grandfather of organic chemistry. He did a lot of stuff with sugars back in the late 1800s, early 1900s. And he wanted to view these sugars in a different view than with all the wedges and the dotted lines. It was very confusing, especially since sugars are very large. So he had a different projection. So rather than having the wedges and dotted lines, he would like take a molecule that looked like this, and he would just kind of put straight lines. And this carbon, that center right there is a carbon, and that's our chiral center. And this is the projection. What this means is anything that is in the vertical axis is going back into the page. You see how it's a dotted line here? All right. And anything in the horizontal plane is coming out of the page towards us. Okay, so instead of writing the wedges and dotted lines, this is the view he would do, and he would just do straight lines, and you'd have a hydrogen here, an OH here, I don't know, an NH2 group there, and let's put a chlorine there. All right, and what this means is that the hydrogen and the OH group are going back of the plane, and then you have and the NH2, that's NH2, and then you'd have an OH here, and you would have a chlorine that's coming out here. Okay, it's kind of like a bow tie is how I think about it. Okay, so Fischer projections, a lot of people think are easier to see. You don't have to worry about any of the wedges or dotted lines. So if you take a molecule like this, okay, notice the hydrogen here is going back and the OH is going back, but then this group is coming out towards you and this group is coming out towards you. So this is the view. So rather than writing the dotted lines and wedges, just write as a straight line. So this would be a straight line and this would be the straight line. Okay. So just a different way of drawing it so you don't have to do the wedges and dotted lines. Some people find it easier, some people don't. I don't know. You can form your own opinion, but you just have to know how to do it. So, okay. Okay, let's now talk about what's called optical activity. These molecules, chiral molecules, have what's called optical activity. This is a physical phenomenon, and it is fascinating that molecules do this. Okay, what actually happens is if you shine light, okay, plain polarized light, into a molecule that's chiral, it actually will shift the angle of the light. It actually bends the light in a certain direction. All right. And that's how you know if the molecule is optically active, if it's chiral. If it's chiral, it will do this. If your molecule is achiral, it will not do this. Okay, so what is plain polarized light and how does this work? Okay, so first of all, you have a light source, which is a light bulb, all right, and light waves are going all different directions. Ordinary light, the wavelengths are going up and down and angular, so all of these are waves of light, are going all different directions. Okay, and they're kind of showing this with the arrows right here. Then you put a polarizer. This is a polarizer, okay? Anyone that has polarized sunglasses, if you ever take like two pairs of polarized sunglasses and you put them one in front of the other and you move the one in front of you, it'll be completely black and you won't be able to see through it. But then if you twist it at 90 degrees, then you're able to see through it. That's because your glasses are polarized. That means they have slits going one direction. Okay, all the other directions are being absorbed into the polarizer. So you have all this light randomly going, but then if you shine it through a polarizer, the only light that's allowed to pass through is the light in which you have the openings on your polarizer. So only light going up and down. Okay, okay. So that's what's called plain polarized light. It's light that's been through a polarizer, and it's only going in one plane, which is the plane that's going straight up. All right. Then you put it through your sample. So here I have a sample tube, and let's say I have one of the enantiomers in there. what happens is the molecule, because it's chiral, actually will shift the direction of the light. Okay, and all depending on which way that the light travels, I have an analyzer here. This is 0 degrees. All right, right here would be minus 90 degrees. Yeah, minus 90. The other direction is positive 90. All right, and the light, it looks like is going, well, it's like this, is going like that. Okay, so I read it off, and that looks like, I don't know, maybe minus 60. Okay, so this enantiomer, let's call it enantiomer A, all right, has a minus 60 angle, or alpha. I call it alpha. So enantiomer B, let's say I were to put enantiomer B in there, what do you think the angle would be for enantiomer B? Enantiomer B. Well, if enantiomer A is minus 60, the B is going to be positive 60. It's going to shift the plane polarized light equal but the exact opposite direction. Okay, and this is a pretty interesting phenomenon that enantiomers have. Okay, achiral compounds do not do this. Achiral compounds are not optically active, and they do not split plane polarized light, so the light will just go completely through at 0 degrees. Okay, if the rotation is clockwise, that means if I have the analyzer and the light is going this way, and I get like a positive like 60. All right. Okay, that's what's called the dextrorotatory, or the plus enantiomer, or the D enantiomer. You remember we saw on the L-DOPA, there's L-DOPA and D-DOPA. Okay, well the D-DOPA is the enantiomer that goes to the right on plane polarized light. All right, if it goes counterclockwise, it's called levorotatory. That's where the L coming from, L-DOPA. L-DOPA, that's what the L's come from, the L or the D. All right, or the L sugar or the D sugar. Okay, you guys might have heard of that in sugars. You also have L's and D's because it just all depends on which enantiomer you're talking about. Okay, so two enantiomers rotate plane polarized light to an equal extent but opposite directions. And the only way you know if you're going to have the plus and the minus, or notice the left hand, this is like the left hand version, and this is the right hand version. That's kind of what we say. The left hand version is the minus enantiomer, or the L for left hand, and the plus is the right hand. Okay, so there you go. That's optically active compounds. Okay, so it's what's called a specific rotation, is the standardized angle for the specific enantiomer. So glyceraldehyde, the L enantiomer has a bond angle, an angle of minus 8.7, and the D enantiomer, or the right-handed form, has a positive 8.7. These R's and S's, your book does not talk about it, so I do not like how they do this. Since now I talk about this in the organic class, in the year-long organic, but in our class we're not going to talk about R's and S's, so I want you just to kind of ignore those. Just kind of know the D and the L and what they mean and where it comes from. It just means which way light splits it. So this enantiomer, if you put in the plane polarized light, is going to split the light positive 8.7 degrees, okay, where the L-glyceraldehyde will go the opposite way. And you can either use plus or L, okay? So this is either minus glyceraldehyde or L-glyceraldehyde. This is either plus glyceraldehyde or D-glyceraldehyde, okay? Let's stop here because 15.8 is a totally different concept.